Okay, hello everybody. Welcome to our Wednesday seminar. And it's my pleasure to introduce our next speaker, Tim Cronin from MIT. He's assistant professor there. And he's got his PhD relatively recently in 2016. Actually, 2014, right?
2014, yeah.
Yeah, 14, sorry. So it's not relatively recently, although it seems like way, because I remember being a student and talking to him quite often at the conferences. So after that, he got his PhD from MIT in 2014, and then he didn't go too far away. So he got his postdoc at Harvard University, where he'd been postdoc for about a couple of years. And then he was offered apparently assistant professorship at MIT back at MIT. So it's almost like Kerry Emanuel's career, right? Who
well, I didn't get a PhD out of what I thought was a master's degree, so it's not quite like Kerry's.
Oh, really? But Kerry got all his degrees at MIT, so, and he's professor at MIT. So that's kind of unique, I think, in many respects. Yes, he's very active researcher. He has quite an extensive publication record, and his papers are always very interesting to read. And he got numerous awards and honors from many places like NOAA and Harvard University and so on. So without further ado, I think we're very fortunate to have him today as a speaker. And Tim, please, we can start now.
Okay, thanks very much for the invitation and the introduction, Marat. So I'm going to talk today about some very idealized numerical modeling work I've done over the past few years, simulating rotating atmospheric convection under a range of dry to moist conditions. So the combination of planetary rotation and moist convection on Earth leads to the dramatic phenomenon of hurricanes or tropical cyclones. And hurricanes as a phenomenon in Earth's present climate are inextricably tied to water. And how we portray them does that justice. So the way we show hurricanes is vividly connected to how they mobilize atmospheric water into a thick swirling cloud pattern, or by the way they've moved ocean or rainwaters near the surface into crashing waves or rain-blasted palm trees or an inundated landscape. Most of the damage from hurricanes also comes not from their winds, but from storm surge and freshwater flooding, the ways that they move water around. I want to say as well, please feel free to interject or put something in the chat. I've got a window open if you've got a question or something's not showing up, just chime in. The basic question that we want to dig into with this research is this: is moisture truly fundamental to the vortex dynamics of a hurricane? This might sound like nonsense in light of the previous slide. How can you imagine a hurricane divorced from an ocean surface without dark clouds, torrential rain, just a swirling wind field and an otherwise clear, dry sky? But based on some work from a paper 10 years ago, the answer to this question is no, you don't need moisture for a hurricane. So the authors, Aga Mrowiec, Olivier Paul-Louis, and Steve Gardner, found that you could readily get a dry storm in an axisymmetric atmospheric model. So shown in the left-hand column here are the vortex that forms in a dry model, and in the right-hand column, a vortex that forms in a moist model. And the top panels are showing the tangential or swirling winds, and the bottom panels are showing the radial or inward-outward winds. So they found that the dry model, which was supplied by heat fluxes from a dry surface that was much warmer than the overlying atmosphere, could attain a similar strength swirling winds, and was found to have much deeper layers of inflow and outflow as compared to a typical moist storm, which derives its energy from the thermodynamic disequilibrium between the surface and atmosphere, which is mostly in the form of a humidity jump and not a temperature jump. So as Kerry Emanuel put it a few years ago, this paper was met in the hurricane community with just nothing, deafening silence. I think it's fascinating, and it brings up lots of questions, which we have few answers for. And some of the work that I'm going to talk about today has been working to address those. So one is, this was an axisymmetric model. Axisymmetric models kind of like to form vortices because that's how they're set up around a center pole in cylindrical coordinates that, it's biased towards vortex formation. A question might be, are these storms even stable, or will they form in 3 dimensions when you simulate the full 3-dimensional fluid dynamics of a convecting atmosphere? Second, what controls their intensity, size, and structure? Are similar theories to what's used for moist storms viable, or do we need to throw those away and use something completely different? Third, and related to that, what does the transition from moist to dry vortex dynamics look like? So I'm going to talk about work that I've been doing today to address these questions. And I always get this question when I talk about the subject. So I want to maybe either nip it in the bud or tell you that I'm not really going to be talking about Earth here. So you might ask, if dry hurricanes, do they exist on Earth? The answer is no. And if not, why should we care about them? So my most compelling answer to this, okay, that was my cat jumping off something nearby, unpredictable, like convection. My most compelling answer lies in simplicity and the use of model hierarchies, or a set of models of varying complexity to better understand the real climate. So a lot of our understanding of how the atmospheric general circulation, for example, works stems from models that don't include the effects of moisture. And it would be great if we could further develop our understanding of hurricanes in a similar way to how we've developed an understanding of mid-latitude cyclogenesis, fronts, baroclinic instability. All of those things can be understood in models without moisture. The possibility also of rotating dry convection organizing into large-scale vortices also suggests that tank experiments or direct numerical simulation might be able to produce these vortices over parts of parameter space. And I find the idea of experimentally studying hurricanes in a tank to be fascinating and potentially really useful pedagogically. I have a student who's working on a project related to both of these, this second and third points. Related to this is the point that if dry rotating convection is all that's needed to produce a hurricane, it may be possible to find them in simulations or experiments of just rotating dry Rayleigh-Benard convection, which I think would be a fantastic link to a huge body of work on this subject of Rayleigh-Benard convection in applied math, physics, and engineering. And finally, vortices like dry hurricanes might exist on other worlds or in deep past climates of Earth, even if they don't exist in Earth's present climate. So we're studying a phenomenon that's potentially quite general to rotating turbulent convection over a surface of large heat capacity. So with that said, the work that I'll talk about today is not happening on Earth in Earth's present climate, but it is looking primarily at 2 ways of exploring this moist to dry transition of turbulent rotating atmospheric convection confined into doubly periodic miniature worlds, or TC worlds. We've primarily used 2 methods of drying out the surface. The first is just to reduce the surface moisture availability artificially while holding the surface temperature fixed. And the second is to make the surface much colder, which reduces the saturation vapor pressure of a water surface and shifts the surface energy balance towards sensible heat fluxes from latent heat fluxes. And I'll go into a short exploration of another dimension of parameter space, the rotation rate, if there's time at the end. So the punchline, what I hope you remember out of this talk, is largely summarized in this figure and in the title of the slide. So first, dry hurricanes readily form in rotating radiative-convective equilibrium. And second, dry storms, so this is showing the moist to dry transition. There are these clear organization of the surface wind pattern into vortices that are coherent and long-lived in the dry limit, as well as the moist limit and some of the intermediate states. So second, dry storms are less intense. These colors are less saturated, indicating that surface wind speeds are weaker in the dry limit than the moist one, while we've tried to control for things such as potential intensity. But they have bigger eyes or regions of maximum winds than moist storms do. And a third nuanced aspect of this is this static panel in the middle. It's sort of towards the right here. The transition from moist to dry dynamics is mostly gradual, but it's punctuated by what we found is an absence of spontaneous genesis over part of the parameter space towards the dry limit in going to a completely dry case. So this is interesting because there's a lot about tropical cyclogenesis that we still don't understand, and being able to switch cyclogenesis off or on in a model by modifying something is kind of a neat tool. Okay, so this talk will have three main parts. First, I'm going to give some background about tropical cyclones, how to make them in numerical models, and then I'll move on to some of the work that I've done, first on simulations of dry hurricanes, and the dry to moist transition is shown on the last slide, and then discussing the sensitivity to rotation rate briefly if there's time. So for the purposes of this talk, a hurricane and tropical cyclone are interchangeable terms. The essence of a hurricane or tropical cyclone lies in its energy source, which is convection driven by a supply of moisture and or heat from the surface. So tropical cyclones are fundamentally different from extratropical cyclones because they draw their energy from the surface. They like symmetry and a lack of wind shear. They're inherently diabatic phenomena that require air to cross isotropes as it circulates through the storm in the inward, upwards, and outwards motion of the secondary circulation of the storm. Extratropical cyclones, on the other hand, draw their energy from large-scale horizontal temperature contrasts. They're inherently asymmetric and form most readily in environments with strong balanced shear. And the flow in them can largely be viewed as an adiabatic exchange of cold air moving downwards and equatorwards and warm air moving upwards and polewards. In the present climate on Earth, hurricanes are limited mostly to the tropics because only in the tropics are these combined factors of weak horizontal temperature gradients and relatedly weak vertical wind shear, as well as a large disequilibrium between the surface and near surface air are those two factors found. Hurricanes also require some amount of planetary rotation to project onto the local vertical direction, which is not true sufficiently close to the equator where hurricanes don't form. And Kevin and Dan Shavas, who's a collaborator on this project, have done some nice work on that subject. So there are some rare exceptions to hurricanes being a tropical phenomenon. There are a few observed tropical cyclone-like disturbances in the Mediterranean called metacanes, as well as polar lows in some Arctic Ocean areas, which have a structure that looks similar to that of tropical cyclones, but is obviously in a way different environment. But for the most part, hurricanes are a tropical phenomenon on present-day Earth, which is part of why they're also called tropical cyclones. So I talked briefly about the idea that hurricanes are fundamentally diabatic and require heat throughput to operate. And this works best in the current climate in the tropics. I want to go into this a little bit more. So the diabatic essence of tropical cyclones means that they can theoretically reach a steady state where the overturning circulation in radius height space, which I'll try to annotate here, looks like this. So you have inflow from distant radii far away from the center of the storm, shown as point A here, towards the center of the storm, or the eye wall, point B. You have intense deep convection in the eye wall, which transports air upwards and which slants outwards in the outflow of the storm, and then slow subsidence back down over much of the outer portion of the storm towards the surface. So each of these three panels, this is in height radius space on the left, in pressure volume space in the middle, and in temperature moist entropy space on the right, is showing a cartoon of this overturning circulation or secondary circulation in a tropical cyclone. This is the secondary circulation because the strongest winds are the primary or swirling azimuthal cyclonic circulation. So in pressure volume space, you can map this to point A being the highest pressure, point B being the inflow leg from point A to B being nearly an isothermal expansion, the ascent from points B to point C being a near adiabatic expansion, and the leg back from point C to A being a combined loss of energy, and so something that's in between an isothermal and adiabatic compression. And so that's compression back to point A. And similarly, in temperature moist entropy space, you can diagram this as an even simpler triangle where the isothermal leg from points A to B is a horizontal line. The isentropic leg from points B to C is a vertical line, and then you have a return leg that's some sort of diagonal or curved path back from point C to point A. And the important aspect of this is that both of these thermodynamic diagrams on the right show that the area enclosed by a cycle here, so underneath this, if you were to shade the enclosed area inside this loop, or the enclosed area inside this loop, is positive, which means that this cycle, this thermodynamic cycle, has the potential to do work, and that's the essence of what Carey-Emanuel's potential intensity theory describes as a speed limit for hurricane winds. So if we zoom in and look at a tiny subcycle near the center of the storm, going from a point right near the eye wall to the eye wall itself, ascending in the outflow, descending a bit and losing energy, and then coming back to this point, this thermodynamic subcycle would look like a isothermal expansion, adiabatic expansion, isothermal compression or near isothermal compression, and adiabatic compression, something like that. This thermodynamic cycle encloses area and thus can do work. And the heat input rate per unit mass of air through this cycle is given by the product of the wind speeds near the center of the storm and enthalpy exchange coefficient CK, and the thermodynamic disequilibrium or moist enthalpy disequilibrium between the surface itself and the air just near the surface. And then the potential work done is given by this efficiency, an efficiency multiplied by this heat throughput, where the efficiency is equal to that of a Carnot cycle, the surface temperature minus the outflow temperature divided by the surface temperature. And so the idea of potential intensity is to then equate this potential work done with the dissipation of energy by the swirling winds near the sea surface, which is equal to a product of CD drag coefficient and the cube of the wind velocity, v cubed. And so equating this efficiency multiplied by heat throughput with the dissipation gives you CD v cubed equals efficiency times CKV times an enthalpy disequilibrium. And then solving for the velocity gives you what we call the potential intensity, which is given by a ratio of enthalpy to drag coefficients, and a thermodynamic efficiency and an enthalpy disequilibrium raised to the half power. So there's a lot of work by Carey-Emanuel on this. And the main thing that I want to highlight is that nothing in the theory that I just presented about potential intensity assumes that there's moisture in the system. The way that the exact way that the ascent leg and the subsidence leg work out in terms of temperature entropy space are affected by moisture, but a similar sort of heat engine that you get could operate in a perfectly dry atmosphere as well. So having defined hurricanes as broadly as possible, we can see that based on this theory of hurricanes as axisymmetric warm core convective cyclones that act like heat engines and generate swirling winds under the influence of rotation, there's nothing essential about moisture in that construct. So dry hurricanes would instead be driven by a temperature jump between the surface and overlying air. So in the real atmosphere, most of this moist enthalpy disequilibrium is because the surface is saturated, whereas the atmosphere above is not. And there's a small few degree temperature jump as well. For a similar intensity dry hurricane to exist, you would need this temperature jump. There would be no moisture disequilibrium, and the temperature jump would need to be 10 to 15 degrees, something on that order of magnitude. So dry hurricanes would also be driven by sensible heating of the inflowing air rather than by evaporation, and by deep troposphere spanning dry convection near their cores rather than by moist convection. And this is exactly how the cyclone simulated in the Mrowiec, Pauly and Garner work worked out. But we want to go a bit beyond that, as I said earlier, by first working in a three-dimensional model to look for possible instabilities or failure of vortices to form due to 3D effects. Second, by using a closed domain, a sort of isolated, confined world, rather than one that has open outer boundaries, which was what the previous study used. And third, by also spanning a range of surface conditions between dry and moist, rather than just looking at dry and moist limits. So in order to do these simulations, we need a minimal model setup that allows for hurricanes to form. Fortunately, lots of people have worked with such setups before. So that minimal model setup starts with the idea of radiative-convective equilibrium. So the real Earth, of course, has variations in surface temperature, continents, land surface properties, spherical geometry. Most of those are unnecessary complications for us. So we're going to set up simulations of hurricane worlds by looking at an atmosphere that's in an idealized thermal equilibrium, where the troposphere has radiative cooling balanced by convective heating, and if it exists, surface evaporation balanced by precipitation. You can also have dry radiative-convective equilibrium where there's no surface evaporation and no precipitation, and dry convective heating balances radiative cooling. And above the troposphere, there's a stratosphere, which is in pure radiative equilibrium with essentially no mixing. This is usually defined by, as I said, by a moist convective troposphere, but we can apply it just as well to a dry convective troposphere. So dry RC looks a lot like moist RC, but the tropospheric heat transport switches from transport by moist convection and clouds to transport by dry convection and just thermals. It's a lot like what you have over a very deep dry convective boundary layer in a desert. You have a stratification as well that will be dry adiabatic in dry RC rather than moist adiabatic. And we just need one extra ingredient to add to RC to get a recipe for a world with lots of hurricanes, and that extra ingredient is rotation. So you just add a Coriolis acceleration in the horizontal momentum equations, and that causes inflow to an area to develop rotation or circulation in a cyclonic sense. So areas with a lot of ascent develop swirling cyclonic winds, and that can intensify into things that look like hurricanes. So when you simulate this in a, this is showing work from, I believe, Held et al. Paper from 2008, but Marat and Kerry have done similar work. Kevin and Dan Shavas have done similar work. Lots of people have done simulations with either convection permitting models or GCMs that show formation of such tropical cyclone worlds. So I think that's this sort of turbulent world filled up with vortices is a cool construct to use. Okay. So I'm going to talk a bit about the simulation of dry hurricanes and this moist to dry transition, which is the main research part of the talk. If anyone has questions first, I'm happy to take them. I'll take a short break for it.
So Tim, is the essential difference, say, between a tornado and this dry hurricane, is it the scale and therefore Coriolis?
So I think it's not the scale fundamentally. There is an aspect of scale that's important, but tornadoes derive their vorticity from tilting shear, right? Mostly, whereas tropical cyclones derive it from ambient rotation. So there is a sense to which you couldn't do that at very large scales and create a massive tornado, right? It would have to be, it would not be practical. But I think the other essential point is that this is not a vortex instability or a vortex that results from an updraft well above the surface that's not really coupled to surface heat exchange. So you could have a tornado perfectly well over an insulating surface, right? But you don't get a hurricane over a surface that doesn't supply the atmosphere with heat, and that's the sort of second distinction, I would say. The question. Okay, I'll move on to talking about my experimental setup and results. So I'm using the system for atmospheric modeling, Marat's atmospheric model, which I've grown to love and use a lot. In a doubly periodic domain with side lengths of around 1,000 kilometers and a horizontal resolution of a few kilometers. We're prescribing a tropospheric radiative cooling that's fixed at 1 Kelvin per day. So we're decoupling the radiative transfer from the water vapor and clouds in the atmosphere, which is a useful simplification for us. And we're fixing the surface temperature in each simulation to so in one set of them where we vary the surface moisture, it will be set, that surface temperature will be set to 300 Kelvin. In another set of simulations, it will be set vary between 240 and 300 Kelvin. And so two ways of going from a moist to dry surface. First, we vary the surface wetness beta, which appears in the bulk formula for surface evaporation, and it as a multiplier on the surface saturation vapor pressure of pure water at a given temperature. So the second way we make the surface dry is by making it cold, which reduces the saturation vapor pressure over the surface and causes most of the heat exchange to become sensible. So one thing to note is that this beta factor is actually physically realizable. And we took our notation from the literature about surface hydrology over hypersaline water bodies. So Raoult's law says that the vapor pressure of a substance in an ideal solution is equal to the molar mixing ratio of that substance times the saturation vapor pressure of the pure substance. So salt water, for instance, is about 3% salt, and the other 97% is water. And so the saturation vapor pressure over ocean water is reduced relative to that of pure water at the same temperature. So the real ocean has about a beta factor of about 0.97. And the Dead Sea and parts of it have values of beta that are less than 0.5 because it's so salty and because there are non-ideal solution effects in play. So in theory, you could get a much lower value of beta if you mixed the ocean water with some non-volatile fluid and the ocean were a liquid that was only a small amount water. Not likely on Earth, but who knows what happens on other worlds. Okay, so without further ado, I want to pull up a movie, and I think I need to, pull this in from. Okay, so I'm going to show two simulations, one of a moist surface, so that's with beta equals 1, and another of a dry surface with beta equals 0. And this will show the evolution of the surface wind speed, ranging from low values in blue to higher values in green and orange and yellow. Okay, so let's see if I can play this. Oh, I need to turn off the annotation. Okay, there we go. So what you see is that this is over. So if the day indicator here is too small, this is about 5 days into a simulation. And the dry simulation has evolved into this sea of swirling vortices. The moist simulation about 10 days in and to 15 days in also forms this sea of hurricanes that swirl around each other, interact, do Fujiwara dances over as many days as you want to simulate. And eventually you reach a sort of pseudo steady state, so that one little vortex disappeared, where there's a roughly fixed number of cyclones. Over time, if you simulate this for longer, some of them will disappear. You'll end up with formation of new ones. And the same sort of thing happens in the dry case. So so a few take-home points for this. First, as I mentioned, and if this is the only thing you remember from this talk, then fine. 3D dry hurricanes readily form and persist in a rotating RCE environment. If you then kind of look at the second order things, the structure and intensity of these dry storms is very different from their moist counterparts. They're about half as large. The peak wind speeds are about half as large for the dry case as the moist one. But the storm wind field, at least where it's relatively strong, extends quite a bit further out from the center. So the eye wall radius is much larger compared to the outer radius for dry storms as compared to moist ones. And maybe sort of surprisingly, given these very large difference in peak wind speeds and structures, the moist and dry surfaces end up with similar domain averaged kinetic energy dissipation. So if you take that CD V cubed and integrate it over the surface everywhere, you find that it's a few watts per meter squared for both of these cases. And so it's a little bit larger for the moist surface, but not by a huge amount. So the broader eyes and larger areas of moderately strong winds in the dry case compensate for the extremely strong winds in the eye wall of the moist cases. Okay. So dry hurricanes look pretty different than normal moist ones in terms of their radial structure and uniformity. For instance, there are a lot of storms in the dry case. So this is showing a snapshot, a map of on the left-hand column. The bottom is showing this dry TC world, and the top is showing a moist situation, the moist simulation. As I mentioned before, they're much weaker, but the azimuthal winds of each storm look very similar compared to one another. So this right-hand column is showing the radial profile of azimuthal winds, and you see that each of the dry storms. So if we identify each vortex separately and look at a composite in radius of its azimuthal wind speeds, they all sort of follow this very similar shape. This simulation with moist storms, on the other hand, shows that moist hurricanes can have pretty different radial structures of winds at similar peak intensities. So one of these storms is small and has a wind field that decays quickly, and another is larger and its winds extend much further out. And finally, the structure of the warm core is dramatically different, with the warmth of moist storms extending, being peaked well above the surface. So these contour lines here indicate the temperature perturbation from the horizontal average. So moist storms have a warm core that's or anomalous warmth that's peaked well above the surface, but extends deep down into the troposphere. The dry storms, on the other hand, have just this tropopause confined warm core, which is kind of interesting. So they have a low surface pressure that extends all the way up almost uniformly to the tropopause, and then the tropopause bows down a bit, causing a warm anomaly there. So we also want to understand whether the transition between these very different structures of vortex is continuous or not. And that's where things get to be interesting and quite confusing. So the storms do tend to gradually transition in size, intensity, and inner structure, except that there's this no storms land where storms don't form at all at low but non-zero surface wetness. So this is showing beta values of 1 for a moist surface, 0 for a dry surface on the right, and then values of 0.7, 0.5, and 0.1 in between. So you see this sort of gradual weakening, decrease in size, and the sort of hollowing out of the core eye wall as you go to beta equals 0.5. So already for a half wet storm, you have vortices that look quite similar to the way they do in the moist case, though they still retain some characteristics to the dry case, they still retain some characteristics of moisture. But at beta equals 0.1, nothing forms at all. You just simulate rotating RC and it stays disorganized as popcorn convection forever. So a way that we could identify what parameter range corresponds to this rather than taking snapshots is to look at the domain averaged surface kinetic energy dissipation. So as I said earlier, that's a number in watts per meter squared that corresponds to the average value of CD, the drag coefficient, times the air density times the cube of the surface winds. And so over a range of surface wetness, we see that the sort of wet storms all have an initial peak in their dissipation that settles down into an equilibrium. As the surface is dried out to this value is beta equals 0.3, which takes the longest to form storms, we still end up with similar values of kinetic energy dissipation, though they're a bit smaller. And then nothing happens so these simulations just flatline with no large scale organization, no persistent vortices for beta equals 0.3 down to 0.01. And then you, on the other side of things at 0.003, 001, and beta equals 0, so the completely dry limit, you end up with formation of dry hurricanes. And the same thing appears to happen as we go from a warm surface to a cold surface. So this simulation with 300 Kelvin is the same in both cases here. The bottom panel is showing the same time series of average surface dissipation, but for simulations where surface temperature is varied across simulations rather than surface wetness. And so at 290 and 300 Kelvin, we form cyclones quickly. At 280, it's delayed by quite a bit. At 270, 260, 250, they never form for as long as I've simulated. At 240, they form almost immediately. So there's a striking similarity between these two sets of simulations. And you might ask as well, okay, if we try to seed a storm into this range of parameter space where no storms spontaneously form, what happens? And the answer is that those storms stick around. So we've done simulations where we ramp surface temperature up or down in time, starting from a world that has storms and sort of maintaining one for a long time period, and found that also found with moist to dry and dry to moist parameter sweeps where we vary the surface wetness in time, that if we start from a world that has cyclones, they stick around through this sort of no storms land parameter space of in our configuration 250 to 270 Kelvin. So what's shown here is that the fixed sea surface temperature simulations have surface kinetic energy dissipation of a few watts per meter squared for the sort of very low temperatures, as well as for the higher temperature ranges where you see moist storms. This range of parameter space in between, where we didn't see storm formation, has very low surface kinetic energy dissipation. But as we sweep, as we increase surface temperature and time, we form this dry cyclone world that evolves gradually to a moist one. There is a sort of valley here, and that's interesting. And the same thing happens as we go from a moist tropical cyclone world down to a warm tropical cyclone world down to a cold one. Okay. So to further characterize and look at this moist to dry transition, and also to provide evidence that storm properties tend to transition relatively continuously between moist and dry limits, with the exception of this sort of abrupt absence of spontaneous genesis, we can look at two non-dimensional quantities, properties of the individual cyclones. So we compile statistics by identifying all the cyclones in each hourly snapshot of our simulation, calculating azimuthal averages for the winds of each cyclone, and then these two quantities. So first, there's the ratio of maximum to potential intensity. And second, there's the ratio, the inner core Rossby number, which is defined by the maximum velocity divided by the Coriolis parameter times the radius at maximum velocity. So this is sort of a normalized intensity on the left-hand side, and this is an inner core Rossby number where much greater than 1 values for the inner core Rossby number correspond to cyclostrophic balance. Values much less than 1 would correspond to geostrophic balance, and values order 1 correspond to gradient wind balance. So we see that both moist storms, so this is showing a series of simulations at different surface wetness and a series of simulations at a different surface temperature on the bottom, both moist storms and warm storms have maximum velocities that are close to their potential intensities, so values that are close to 1. But as you dry out the storm or cool the storm, you decrease that ratio. And by the time you're at beta equals 0.5 to 0.4, you are already at you're at about 0.3 for this ratio, which is the same as the dry storms attain. So this is a gradual transition as the surface is dried, and then this sort of punctuation by a range where no storms form, then the same values emerge on the other side of that no storms land. And similarly for inner core Rossby number, you have cyclostrophic balance hold well for both moist storms and warm storms, and there's a gradual transition towards gradient wind balance, weaker winds, as you go towards the dry case. Okay, and this transition. So the point, really the point that I want to make is this transition is not between a block of moist storms all with one set of properties and a block of dry storms with very different properties and a discontinuity in between. It's really a transition that mostly happens as you go through this semi-dry range and not through the no storms range. So that should, give us some confidence that these dry storms are fundamentally the same thing that's happening in the semi-dry limit, and that's part of a continuous parameter variation that gives you moist storms. Okay, so again, main results of this: dry hurricanes readily form in rotating RCE. Their properties differ from their moist counterparts. They have weaker peak winds, larger radii of maximum winds relative to their outer size. And the transition appears to be relatively continuous, except for this no storms land barrier to spontaneous genesis. Okay, so I think I have a bit of time where I want to talk about sensitivity to rotation rate. So this is one of many more questions that spin off from this work and that I'll cover in a small amount of detail. So this started with a fun question, which because we wanted to fit more storms into the box. So knowing that if we increased the Coriolis parameter, the length scale for storms would decrease, we wanted to ask the question, what if we spun it faster? So I showed results already with a pretty rapid rotation rate before of 3 × 10⁻⁴ inverse seconds for the Coriolis parameter. I'm now going to show results with about a 3 times larger rotation rate. So I'll pull in the movie for that. Okay. So this is now a moist surface on the left and a dry surface on the right at a very rapid rotation rate of 10⁻³ inverse seconds. So now storms form in the moist system faster, but something qualitatively different happens for the dry case. You don't end up with a world that's full of closed off vortices. Instead, you see a sort of field of swirling turbulence that looks, to my eye, a lot like what you expect something like sort of geostrophic turbulence to look like. There's energy injected at small scales from convection, which winds up as swirling circulations at much larger scales. And so something also very funny happens towards the end of this simulation. We end up with just one cyclone in the moist case, but as we continue to go on in time, it weakens, sort of falls apart, and you'll see towards the, I think a few seconds now, this cyclone is actually going to spit out 2 cyclones. So there's one. No, not yet. So this hurricane has weakened a lot. So there's one starting to form, and then there's another that gets spun off of it. So this is like a cyclone splitting process that's odd, and not something that we see in most other simulations at lower rotation rates. So the dry case appears to be qualitatively sensitive to rotation rate, in that you end up with a very different solution at very high rotation rates. The moist case might be as well, but we haven't tried to push it to Coriolis parameters much higher than this. But it seems like there may be strange behavior starting to happen. Okay, so our hypothesis about what's going on with the dry case and why we stop seeing cyclones here is that we think that dry hurricanes can't form at a sufficiently small convective Rossby number. So for a dry convective system, the convective or natural Rossby number is given by, it's essentially given by a ratio of the time scale it takes for convective ascent through the depth of the layer, that the rotational time scale divided by that. So in Earth's atmosphere, convection is much faster than rotation, so you end up with large convective Rossby numbers. But if you increase the rotation rate enough while not changing the depth of the layer or changing the surface buoyancy fluxes, you make convection comparable to and eventually slower than rotation. And so this is thought about in ocean convection, where deep convection in the ocean has a time scale for parcel sinking that's comparable to rotation. And as a consequence, individual convective events develop balanced circulations associated with them. You don't see just sort of popcorn convection, you see strongly rotationally constrained convection. And regime transitions have been observed with varying convective Rossby number in other experiments and simulations of dry convection. So if we look at a bunch of different rotation rates, varying from 10 to the minus 4 at the top left to 2 times 10 to the minus 4, 3 times 10 to the minus 4, 4 times 10 to the minus 4, 6, and then 10 to the minus 3 down here, the convective Rossby number decreases from about 4 to about 0.1 over that range of parameter space of rotation rate. And we also see a concurrent breakdown of this organized, nicely tiled or turbulent tropical cyclone world into something with very little large-scale organization in sort of strong cyclone, tropical cyclone-like features. So ongoing work consists of sort of going into whether moist storms are also susceptible to being to breaking down in a similar way as we increase the rotation rate, or if not, why moisture prevents this from happening. Okay. So I think that brings me, terrific to summary and conclusions. So I talked a little bit in the introduction about extending existing hurricane theory to the dry limit, and then showed through a number of simulations that dry hurricanes readily and rapidly form in dry rotating RCE. The moist to dry transition is pretty interesting. It's not continuous in terms of spontaneous genesis, but across the whole range of boundary conditions, the cyclones are able to be supported once they form, and semi-dry storms look a lot like fully dry ones in non-dimensional parameter space. And finally, from this rotation rate suite of simulations, there appear to be some interesting global flow transitions near convective Rossby number 1 for dry, but not for moist surfaces. We're still working on investigating that. So sort of to close, taking a step back, most of the idealized modeling work on tropical cyclones is focused on sort of realistic parameter space ranges near these thick black lines. So I'm showing 3 axes here of parameter space: sea surface temperature, surface wetness, and rotation rate. What I've looked at, sampled sparsely in my work today, is this sort of these 2 green lines, one extending at somewhat higher rotation rate than we see in the real world from wet to dry, one extending down from near tropical surface temperatures to much colder, and then another one that should be here is extending upward to high rotation rates.
Show me your without show me.
Other work has suggested that there's this distinct hypercane instability at very high sea surface temperatures. So to close, I think that there's a whole lot of room to push the boundaries of what we do in idealized simulation of hurricanes, that there are numerous signs that there's pretty interesting territory in many directions, and we can learn a lot from exploring it. So thanks for your time, and I'm happy to take questions.
Thank you, team. Do we have the questions?
Yeah, I have a question. This is Ming.
Yeah, sure.
Meanwhile, yeah.
Go ahead.
Yeah, so this is very interesting. Can you tell us why there is this break? Is there like an intuitive explanation regarding the break?
So thanks for the question, Ming. We tried to figure out a good explanation for it and spent a while and didn't come to a compelling explanation. My best guess at present is that it has to do with how precipitation evaporation affects cyclogenesis across a range of different parameters. So that can sort of explain what happens in the dry to moist transition. The warm to cold is a bit different and is a little confusing because of a transition from rain to snow. And then the way that precipitation forms at very low temperatures in SAM is just through ice sedimentation of clouds themselves. But in any case, as you go through this intermediate parameter space, the precipitation efficiency gets very low. So a reason for that is that I can zoom in on this right-hand panel or focus on this right-hand panel for now. The precipitation flux as a function of height is for moist RCE has a peak, at a little bit above this in the cloud layer for shallow clouds, and then a decrease below. So there's net evaporation here in the subcloud layer, and there's net condensation above. For the sort of fairly dry simulations, the boundary layer, the dry convective boundary layer deepens, the moist convective cloud layer shifts upwards, and it's very hard to get rain to fall through a deep dry adiabatic layer. And so as a consequence, if you develop surface convergence and ascent in these sort of intermediate but low surface moisture cases, you'll probably end up raining a lot into a dry layer beneath, causing a lot of downdrafts and killing off your surface convergence. That's our hypothesis. The way that it applies to the fairly cold case is a little bit is not so clear.
Mm-hmm. Yeah. So another quick question. You impose the 1 degree cooling radiatively in the
That's right.
atmosphere. I wonder if that cooling rate is larger when you increase the rotation. Where you get a hurricane, do you expect to get a hurricane in like the geostrophic turbulence simulation?
So based on the convective Rossby number, I expect that it would, because in RCE you need in dry RCE, you need the sort of integrated cooling of the troposphere to be balanced by the sensible heat flux. So a larger cooling rate would lead to a larger surface buoyancy flux in equilibrium. And that would translate to a larger convective Rossby number. So my guess would be yes, but we haven't tested that.
Yeah, so that would be a complement to what you have done.
Yeah,
with
that's right.
The F.
Yeah, so you could attain a very similar value of a convective Rossby number with a bunch of different combinations and our hypothesis is that this is an important parameter for the dry hurricane worlds, but it's not. We haven't mapped it out thoroughly.
Thank you.
Okay, Edmund.
Hi, this is Edmund Chen. Very interesting talk. So I have another question. So based on what you've seen, it seems that dry hurricanes can form. So is it possible for something like that forming in the deserts, for example, or is the desert a parameter space that they don't form spontaneously? Or
so I think that's a really good question. My guess about that is that it's certainly possible if you think about this typical daytime soundings over a really dry desert area like the Sahara. You can get dry convective layers up to 500 hectopascals. That's certainly a big enough scale to develop something like this. The issue is that the surface boundary condition over deserts is not close to the same as what we've simulated. It's not a fixed temperature condition. It's a low heat capacity surface that can heat or cool rapidly. And so, you know, at night, these cyclones take multiple rotational periods to form. At night, the surface cools off, and it's not clear that you could sustain over multiple diurnal cycles, you know, a surface that's really warm enough warm relative to the atmosphere to give you this surface wind driven vortex. That's my my sort of hand wavy answer at that. So I think if you could make for a very different, you know, a surface that stored heat much more efficiently, that was desert-like, maybe it would be possible. Or you know, maybe it's possible that even with the diurnal variability, you could see a persistent surface disequilibrium that allowed you to draw heat out of the surface at all times of day.
Yeah, let's hear questions from a student. June.
Hello, can you hear me?
Yep, I can hear you.
Yeah, thanks for the really great talk. I remember looking at the very similar hurricane structure over at Jupiter's pole. Have you ever like looked into any possibility of like similar mechanism would actually be applied to like gas giants?
Yeah, that's a really good question. I've wondered about whether that's possible. I think that there's a lot of uncertainty about the depth of the convecting layers there and whether or not the vortices that are observed are part of the convecting layer or above that. I've talked to some people who have worked on dynamics on gas giants, and I've wondered this. Jupiter's rotation rate is actually close to the value that we've used here for our simulations, which is pure coincidence. But it seems very possible to me.
Yeah, and also it is known that the gas giants are pretty dry compared to the Earth atmosphere. So I wonder if that could also be a clue to find a real world example of this study.
Yeah, it's a great question. That is, I think, the area within the solar system that the other complication that I'm forgetting to mention is that when I've talked to people about this, they say, yeah, but there's no surface underneath. And that makes the dynamics pretty different and more challenging to think about. It's not impossible that there would be surfaces within gas giants due to mixed temperature compositional jumps. So you could have a denser gas composition inside that was warmer and still have it be stable. But I don't know that people think that actually happens, and I don't think we've measured it.
Okay, all right. Thank you.
Okay, last question by Ping.
Yes, thank you, Marat. Thank you, team. Very nice talk. I have a question about this semi-arid hurricane situation in your experiment. In that situation, do you still have the latent heat release from the atmosphere since it's semi-dry?
Sorry, in the semi-dry case?
Yeah.
Yes. So in the semi-dry case, I can go back to this this slide as well, which shows the transition from moist to dry RC in non-rotating simulations, which I've used to initialize all of the rotating ones. So what happens generally is that as you dry out the surface, the dry convective boundary layer it deepens a lot. And you still have a cloud layer where there's moist convection and heat release above that until you get to the very driest surfaces where the near surface specific humidity is such that the LCL is above the tropopause. So as long as there's any moisture in the simulations at the atmospheric latent heat release is unaffected by the surface boundary condition. It's just an aspect. Well, I shouldn't say it's unaffected. We haven't tweaked that part of the model at all, but we've affected the amount of moisture available to clouds by modifying the surface boundary condition. Does that make sense?
Yeah. In this, well, my question is, in this case, if we still consider this as a heat engine, will be the conversion efficiency from heat to kinetic energy will be more efficient or less efficient, about about same compared to the full moist situation?
Okay, great. Yeah, so the efficiency, the global efficiency is similar, but the sort of peak wind efficiency is quite a bit lower for the dry case. So that's what this is. All right, I think a plot. This is on a log scale, so it can be a bit distorted, but there's a very similar global kinetic. So if you average over all space, surface kinetic energy dissipation from winds in the moist and dry cases, it's a bit larger in the moist case, but the surface heat of flux is also larger in the dry case. Sorry, in the moist case. I spoke several times there, double negative. But yeah, so the conversion efficiency to peak wind intensity is lower for the dry case, but the global efficiency of sort of convection as a heat engine is similar.
Okay, great, thank you.
Okay, thank you, Tim, for very interesting talk. And generally, it's really very interesting to me, obviously. And I think it may inspire some future work. And if there are no more questions, we unfortunately don't have virtual lunch. Nobody came up with how you would do that. Maybe we just eat something via Zoom. But I think we're done here. So thank you for coming.
Okay, thanks, Marat. Thanks, everyone. I really appreciate the questions. Yeah.